Okay, let's go ahead and get started here. So earlier I showed you guys how to set up a time-dependent model, and we're going to build off of that again today. And so just to start out, I'll go ahead and reset up that model. Okay, again, it was a solid mechanics model. So this is I'm just going to rebuild what we did last time. Again, it's a time-dependent model. So I'll just go through the model builder wizard real quick and reset up that scenario from last time. So if you recall, we made a beam that was 5 meters by half a meter that looks something like this. Okay, and we made it out of nylon. Again, I'm just repeating what I did last time, but going through a little bit quicker. Okay, and if you recall, we set up a fixed constraint on one end, and we set up a boundary load on the other end. And if you recall, this load was time dependent, okay, meaning it changed with time. And we called that load of t, okay? And we defined load of t up here in the global definitions using an interpolation. Okay, we call the function load. And we set it up starting with at t equals 0. The load would be equal to 0. And then 1 second later, it would be pushed down with 500 newtons. Then another second at t equal 2, it would be negative 500 pascals, that's newtons per meter squared. And at 3 seconds, it pushed up with 1,000 newtons. And I'll go ahead and fill in the rest here. So at 4 seconds, again, it held it at 1,000 newtons. 5 seconds, it reduced the upward force to 500. And at 6 seconds, it holds that at 500. And then at 7 seconds, it starts pushing down again with a negative 500. And at 8 seconds, it holds it at that negative 500. Okay, so this was our time-dependent load that we defined. Again, you could, if you collected, you can manually type in this data, but if you collected this data from some instrumentation, some sensors, you could import it as well, okay, if you're trying to model something. Okay, so let's just take a quick look at this data. So again, at t equal to 0, it has no load, so so it would be just 0, and then 1 second later it's pushing down, okay, and then it starts pushing up, and then it has a little step here, and then it comes back down, okay. And if we come to our study and our time-dependent study, we're going to run this. Last time we ran it for 8 seconds. Okay, so we'll run it again for 8 seconds, and we'll want to plot the results while solving. And with that, I'll go ahead and compute the study. And so this is the same time-dependent study we set up last time. So here it's bending down, then it's bending up, as we would expect, and then as we expect, it comes bending down again, okay? And we plotted the results by right-clicking on results, adding a 1D plot group, and then right-clicking on the 1D plot group and adding a point graph, because we want the data to come from a single point And we selected the point to be the tip over here. So I'll just select that. Okay. And what we selected here was the solid mechanics, the displacement in the y-axis. Now if I click plot, I can go ahead, we can see the results here, and it is as we expected. Deflecting, or the displacement is bending down, and at t equal to 0 seconds, the displacement is 0, but then at 1 second, when we push down on it with 500 pascals, it bends down, and then when we start pushing up on it with 1,000 pascals, it bends up, and then when we have this little step, when we reduce the upward pressure to 500, it ends up right here, and then when we start pushing down again at with negative 500 pascals, it ends up here. Okay, so this is what we did last time, and this was very basic setup of a time-dependent model. And so let's take a look at what happens if we don't start with an initial boundary condition of a load at t equal to 0 of a load equal to 0. So let's just go here and change the load at t equal to 0. What if we start by pushing up with 1,000 pascals? What would we expect the results to be? Well, we would expect the displacement to start up here, right? And then at 1 second, when it starts pushing down with negative 500 pascals, we'd expect it to come down here, right? So let's take a look at what happens if we change this to 1,000 pascals up here. And let's rerun the model. So I'll just click on study again and press compute. And let's take a look at the results. You see how it's kind of jumping all over the place? This is not accurate. This is not correct. So let's talk about why. What happened? Now let's first take a look at the results here. So I click on the point graph and take a look at the results. They don't make any sense. They're kind of just, they look like noise. That's because it is just noise. So what happened here? Well, what happened is the initial boundary condition we changed from 0 to 1,000 pascals. So by default, COMSOL assumes that the initial boundary condition is 0. So at t equal to 0, it assumes the initial boundary condition is 0. So if you change the initial boundary condition from anything but from 0, you'll get this. This is an error. This is a inaccurate model. Okay, and it's not as we would expect. Okay, so what do we have to do? How do we fix this? Well, because COMSOL assumes the initial boundary condition is 0, and in this case, it's not. The initial boundary condition at t equal to 0 is 1,000 pascals. What we need to do to correct this is add an additional step or an additional study to this. So to do that, we'll right-click on the model builder here and add a study. Click on add a study, and we're going to add a stationary study. Now normally this would be done before you do your time-dependent study, and this stationary study, I'll right click on it and add it to study. The purpose of this stationary study, okay, is to get the initial boundary condition. So I'll go ahead and close this section here, okay, and like I said, the purpose of this second study is to get the initial boundary condition. So what we'll do is we'll change the boundary load here to the initial t equal to 0. Okay, so I'll just change that to 0. And if we come up here, okay, the load is already at t equal to 0. The load is 1,000, pushing up. Okay, I can go ahead and compute this stationary study. So I'll press compute, and notice, so it for this t equal to 0, it's just pushing it up. Now this is what we expected. Okay, and notice here in the results under data sets, now we have 2 data sets. Solution 1 belongs to study 1. Solution 2 belongs to study 2. Okay, so now with study 1 being the time-dependent model, we need to point it to the study 2 for the initial conditions. Okay, so here under the values of the dependent variables, if I expand that and I check this box, initial values of variables solved for, right now the method is to use the initial conditions as 0, but that's where we get the error, okay, because the initial condition is not set to 0, it's set to 1,000, pushing up. So if we change this to this method of solving for the initial values of the variables to solution, and then change it to this study number 2, which is a stationary study, okay, and also do the same for the values of variables not solved for, we'll select solution and change it to study number 2. So this is going to point, when we run this study, this time-dependent study, it's going to point it to study number 2 first and get the initial solutions from this solution number 2, okay, which is a stationary study at t equals 0. Okay, so like I said, normally you would set up this stationary step first and then set up your time to, and so you would set up the stationary step first and get your initial conditions, then you would set up your time dependent study. In this case we did it backwards, just to show you how it doesn't work, and how the model can crash if you if the initial boundary conditions are not set to 0. Okay, so now that we are pointing this time-dependent study to solution number 2 to get the initial boundary conditions, we can go ahead and recompute this time-dependent study. So I'll right-click on study 1 and press compute. Okay, and let's take a look at the results. Okay, now notice it's pushing up as we would have expected. Oh, we made a little mistake here. It didn't change anything. Why didn't it change anything? It's because we didn't change our boundary load here back to t. Okay, so right now it's still just set at load of 0. Okay, we need to change this back to t so that it goes through all the time steps here. Okay, so let's run that again. I'll right click on study 1 and press compute, and let's see, it starts by pushing up, then down, and then up, so this is looking correct, and then it should come back down. Okay, and there it goes. So this is what we would expect. And if we take a look at the results, okay, we can see, okay, that at t equal to 0, it's no longer, the displacement is no longer at 0. Instead, it's bending up. And that's what we would expect to be correct. Okay, and then after 1 second, it starts pushing it down. Okay, and then at 3 seconds, starts pushing up again, and then it goes back down. Okay, so this is an important step when it comes to a time-dependent model, that you first have to do a stationary model first if the initial boundary conditions are not set to 0. And then you can set up the time-dependent model, and you have to point the time-dependent model here. You have to point it to the stationary study. Okay,